Hi everyone, I hope that you're all doing well. In this lecture, I want to discuss with you the theory of dummy variables, aka indicator, binary, Boolean, or even Bernoulli variables. They all mean the same thing, which are ways of transforming nominal and ordinal variables so that they are suitable for analysis in ways that we have so far learned are only appropriate for quantitative variables. I'm skipping over some announcements that are specific to the exact version of the course during which I'm recording this lecture, which is Sociology 60 Spring 23 at UW-Madison. Here's the plan for the lecture. Some of this is going to seem specific to the data analysis project that I have my students do in this course, but if you're just conducting a general type of data analysis project, you'll see that many of these things are basically, general techniques. So we'll go over the general motivation for dummy variables and some mathematical properties. Then we'll talk about the first use, which would be that they can make contingency, aka two-way tables, simply look a lot nicer and easier to interpret. We'll have an interlude on making them in stata because this is a case where we really need to understand the theory of the programming that we're doing here. We'll talk about another use case, which would be using them to look at conditional means for a set of groups defined on some variable which we might care about, which also basically comes to the same thing as controlling for that variable in a regression analysis. So for instance, looking at the mean income by race, something like that would be an example of what I'm talking about. We'll also see that even at our level, without going too deep into multivariate analysis, we can use dummy variables to come up with some nice ways to think about multivariate analysis. And then I'll also talk a little bit, time permitting, I'll get to it in this video, maybe not in lecture, the use of dummies as outcomes in regression, which opens the door to the study of limited dependent variables, which is an interesting topic at higher levels. So let's talk about dummy variables. What are they? They're a way to express qualitative variables semi-quantitatively. And in fact, we can say it's really truly quantitative, it's just very limited. You'll see what I mean in a moment. So what we do is we turn a polytomous, which is a term that's very helpful, even though it's a little jargony. It simply means many category qualitative variable that we care about into a variable that takes on just two values. Specifically, what we do is we assign people who fit some criteria on the value of 1 and people who do not fit it the value of 0. So this is the point of a dummy variable. We take some variable m that takes on many possible values, say religion, and those values are in this general set, little m, and little m isn't bounded. And we turn it into a dummy variable on which individuals take values only 0 and 1. So what are some examples? A respondent does or does not have cancer. A car is or is not imported, shades of the Stata Auto data set. Someone is or is not retired. Someone is or is not Catholic. Someone is or is not alive. So these are all examples of dummy variables. So why would we do this? Well, it does two really nice things for us. First, it does away with the problem of directionality for nominal variables. What does that mean? That's a lot of jargon. So note that any arbitrary value assigned to something like religion is meaningless. The GSS does assign numbers to the variable relig, but we know that those don't have any actual meaning. However, if we come up with a dummy variable in Stata called, say, Catholic, and you have a 1 on Catholic if you answered yes to the, you answered Catholic to the relig question, and then you're a 0 if you answered anything else, then there is a directionality here. Going from 0 to 1 means getting more Catholic, and going from 1 to 0 means getting less Catholic. So that problem of nominal variables is dispensed with here. We also do away with the problem of unit distances for ordinal variables. So recall that the gaps for something like a Likert type item, feeling happy or not so happy, neutral, sad, very sad. Note that the gap between feeling happy and not so happy is typically represented in standard, ways that surveys are coded as, say, from 5 to 4, and then from not so happy to neutral might be from 4 to 3 or something like that. But there's no guarantee that those represent identical quantities of, say, well-being or something like that. Those are just numbers assigned. And even if you tried to finesse it and say, well, maybe it's actually about 4, what if an individual, for instance, feels that going from one to the other actually is worth a value of 2, something like that? So this is not as problematic when you ask people something like, are you happy or are you sad? So comparability across individuals is still tough. So what it means for someone to go from happy to sad might be different depending on the person, but for any individual, there's only one distance. So we're not trying to compare, say, going from pain from 1 to 2, 2 to 3, like those questions you get in the doctor's office, we're saying, are you in pain or are you not? And there's nothing to compare it to. So we do away with that problem. So for our class, here are some reasons why we would want to use dummy variables. Two-way tables, or formally conditional distributions, or contingency tables are easier to interpret. Differences between conditional means for groups are also often a lot easier to interpret. It does away with certain problems that we'll get to later. And if you do have the rare case where you've got a qualitative outcome and a quantitative predictor, making the outcome a dummy variable eases the pain. So it's still challenging, but it's the difference between doing something called logit and doing something called multinomial logit, or at least those are two common options. And as fiendishly difficult as a logit can be in some cases, it's much easier to do that. So it's best if you can have just a binary outcome. Here are some examples of these, and note that these are all going to parallel things over here. So a simple cross-tabulation of labor force participation and region on the GSS may be hard to summarize. We'll see an example of that later. A simple difference in conditional means of education by religion is also hard to summarize. And again, this basically has to do with the fact that these variables have many possible outcomes on the GSS. And something like regressing marital status on income is very hard to do if the outcome is not binary. I probably should have made this one a not. I'll probably fix that, but you get the point. So here's another kind of justification at a higher level. If you look at a table like this of regression results, which you may have seen before, you may not have, but basically what this is showing you is when people say, well, controlling for, say, someone's the metropolitan size, I think that's what that is, or the fact that someone was in the Northeast, or that they were in the South, or that they were Black or Hispanic, we estimate that their experience had this impact on their wages. So when you hear sociologists talk like that, you might wonder, how the heck can they control for, say, being Black or being from the South? Those aren't quantitative variables. So in order to control for those things, we actually do need to use dummy variables, and something like this here, this variable Black or Hispanic or South or Northeast or has a college degree or not, those are all dummy variables. By the way, dummy in this context has no pejorative meaning, so I don't want it to seem, because we often associate dummy variables with like race and gender, for instance, I don't want it to sound like we're disparaging the impact or the meaning of those variables. Dummy variables is just one of those terms that, much like regression, has some kind of origin that makes sense, but that original context has really been lost. So I'll oftentimes refer to them by their more formal term or name, which would be Bernoulli or binary or Boolean variables. Those are all the same thing with slightly different contextual meanings, but those are a little bit more precise. So now I do want to introduce you to dummy variables as Bernoulli variables. So nothing new here. We're just going to review some nice properties. So the mean of a dummy variable is the proportion of people who have the property associated with a 1, and I'll show a proof in a second on the right. This is true in the sample and the population. And the population variance is also a really nice quantity. It's p times 1 minus p, where p is the proportion of people that take on that value, or in other words, it's the mean. The standard sample variance calculation has a slight upward bias. You can see the footnotes, or actually the appendices for a proof that I wrote up. This is basically thanks to the Bessel correction, but we actually don't have to really worry too much about that. So the sample variance is effectively the proportion of people that take on the value of 1 times the proportion of people that take on the value of 0. By the way, oftentimes 1 minus p is denoted q, and q just denotes the probability of not being the thing. So for instance, if you have a dummy variable that indicates whether you're a citizen or not, let's say that's about 90 to 10, p would be 0.9, 1 minus p, which is also equal to q, would be 0.1. And the nice thing about dummy variables is those numbers have to sum to 1 with rounding error. So I wanted to walk through this proof because I think it's actually quite interesting. So let's look at the mean of a dummy variable, which will denote d here. And this is the formula for the mean that we've seen before. Note that n to the negative 1 here just means that this is eventually going to go in the denominator, but I often like to write it out front here when it doesn't play a role in the proof, as it rarely does. And this notation here just indicates that di only takes on values between 0 and 1. So any individual can only have a value between 0 and 1. Okay, so how would we construct the mean? Well, we just listen to the summation operator, and it tells us to sum from individual 1 to n the value of di. Now, a nice way to decompose this is to figure that there's only going to be 2 possible values, and regardless of the order that the people come in the sample, we can reorder them. as long as we reorder all of the data. So if you have, say, a matrix of data with, say, 6 columns that indicate variables, as long as if you resort column 1, you resort column 2, 3, 4, 5, and 6, the actual order of subjects doesn't matter. And the vector space operations that we've talked about that are so important won't change if you make sure to sort every column. Unfortunately, most statistical software makes that totally foolproof. There's no way for the user to break that. So anytime you sort on one variable, the program will sort everything else as well. So that's just a nice point. So we might as well assume that they're sorted on the value of this variable. Okay, so then we're going to have 0 sub 1, so the first person who's a 0, 0 sub 2, and then we'll get all the way up to 0 sub n sub naught. And really what that just means is this is the subsample size of people that answered 0, and then we'll do the same for 1. So we have 1 sub 1, the first person who answered a 1, 1 sub 2, etc., up to n sub 1, and that's the sample size or the subsample size of people who said yes. And note that these all sum to nothing, of course. So this is 1 added up basically n sub 1 times, and I wrote that like here. And of course, that's just going to be 1 plus 1 plus 1, etc. And we're just going to get up to n sub 1. If n sub 1 is the proportion of people who are 1s, then we just divide by n, and, the number of people who are 1s. So then the number of people who are 1s divided by the total number of people, of course, is just the proportion of people who are 1s. So the mean of a dummy variable expresses the proportion of people that take on whatever status we coded as 1. And we'll talk about coding conventions later on. Here's an example of what the sample variance looks like. There's a proof in the appendix. But again, the point is that this correction becomes basically increasingly irrelevant, and this is sort of the take-home message that the variance is effectively the proportion times 1 minus the proportion, which is a nice property. We'll come back to that later. So let's talk about use 1 for indicators. Again, indicators are a synonym. They can help us simplify contingency tables. So we already know how to use two-way tables, but sometimes when we have these really highly polytomous variables, two-way tables are hard to interpret. So let's suppose that we're interested in the relationship between labor force status and region. We might construct the following table in Stata. I've seen tables like this already in the homework. I see them every semester teaching this class. It seems intuitive, you feel like you're doing the right thing, but this is really hard to read and makes very little sense. Even if we add in percentages, whether we go column or row, probably we should go here column, because presumably your labor force status is unlikely to cause your region, although maybe not. But even if we add those column conditional probabilities or percentages here, this is still going to be really hard to make sense of. So even if it weren't a mess, we might also just want to, investigate a couple of possible values of each variable. So let's say we're interested in whether someone is from the South and whether they're in the labor force. So we can use dummy variables to find a solution to that. So this is what that would look like. This is the product of that. Note that I have here LFP for labor force participant, and I have not a labor force participant, labor force participant. So these are the two possible values. And the two possible values of South are non-Southerner and Southerner. And we can see here that there's not actually much of a relationship, but that's okay, because what we want to do is just print honest summary statistics when we, when we have the ability to. We don't want to cook the data. So I just made up this example a few semesters ago and like it, and didn't want to change my slides, even though it's not that interesting. Sometimes that's how the analysis works. Note here that we would code this, and I'll show you how to do this soon, so that Southerner, we have these value labels here in Stata. So we don't actually see the zeros and the ones, but mathematically under the hood, this is coded 0, this is coded 1, this is coded 0, this is coded 1. And it's very conventional to make the variable name a possible value of the dummy variable, which you then code as 1. So South indicates being from the South. You should be a 1 if you are from the South, and the same is true for labor force participants. You'll see if you end up doing this for your project that with a little practice, this is pretty quick and pretty easy. So let's look at some Stata code for this. So here we use the GSS 2018. And I pulled up a log file here. I don't often show code in lectures, but the construction of the variable is pretty key, so I want to show how we made that labor force participant variable. So our first step is to get the value label from the GSS, and we'll use the command describe for that. And you can see that the describe prints the value label here. Confusingly, in this case, it's called labd, labeled DE. I'm not sure why. Usually in the GSS, it's the variable, but in all caps. But This is the value label, whatever it is. So you can see then when we write label list lab D, we get this list here, and this is basically a dictionary or a code that tells Stata how to link numeric values, which are the kind of fundamental underlying values, and the values in the label sense, so that someone was working full-time or working part-time and so on. So then we're going to make a new variable called LFP, and I'll describe the construction of that in a moment. What I want you to note first is that we need to look and see what numbers should people have on our new variable. So labor force participants are typically defined as people who work full-time, part-time, temporarily are not working, are unemployed and laid off, but presumably seeking work. Those who are retired, in school, keeping house, or doing something else, possibly, it's actually not immediately clear to me what that would mean. It's probably just in there to mop up, should not be included. Okay, so let's go ahead and make that new variable. So there's a lot of ways to do this in Stata. The most convenient way is to use Boolean expressions. So you can make a new dummy variable in the following way. You say gen new var equals, and then the condition you want to be true of the ones. This will assign people for whom the condition is true to 1, and for those for whom it is false to be equal to 0. Sorry about that. This computer, I have a new computer, I like it a lot, but unfortunately all of these MacBooks just, the slightest touch brings up something you didn't even know existed on the computer. Okay, so then we have the condition here that we want, which is that the person should take on a value of less than 5. Then we just need to think about, is there any way for this to be false? And so what this is going to do is assign people who have a work status of less than 5 to 1s, and it'll assign people who have a work status of greater than 5 equal to 0. Now, here's a problem with that. There are other ways for this to be false. You notice here that there is a .i and a .n. What these mean in Stata, these are missing value codes, and these missing value codes are understood by Stata internally as arbitrarily large numbers, which is really frustrating at first, and it's a very weird Stata gotcha, but it is how Stata works. So what that means is that one way for this condition to be false, so for work status to be less than 5, is for it to be infinitely large. And that's actually true of these people here. So since we had a couple of people whose work status was originally missing, when we write the following code, and I guess I didn't put this down there. When we write the following code, replace LFP equals dot, if missing, that actually assigns those two people who were missing on the original variable to missing on the new variable. Evidently, they had been assigned to zeros actually when we wrote this command. So that's a potential problem. So then we want to check our new variable. To do so, we tabulate our new variable against the old, so we actually just make a two-way table, but here we're just checking our work, so this is not a statistical analysis proper. So note that people became 1s here on this labor force participation variable if they were working full-time, part-time, temporarily not working, or unemployed and laid off. That's the only way people became 1s, right? So none of these people down here became 1s, and none of these people down here became 1s, so that's good news. Then how do people become zeros? Well, the only people that are in the 0 column have these rows, which means that, to be clear, these are counts. So there were no people in the sample that ended up as zeros if they had any value other than these 4, which is good. And then how did people become missing? So there was only 2 people that became missing, and the only way for that to happen was that they had a missing on the original variable. Then finally, our next step is we want to make a value label to prettify the results and make sure that we can kind of do a spot check. So we write the following code. This is a little annoying, but it's a good thing to know. Label define. We can then write any name that we want for the label. Let's just write LFP lab, simple. Then the syntax is a little weird. We write the numeric value, then the value label, then the numeric value, then the value label, and we just keep going as long as we need to. In this case, it's a dummy variable, so there's just 2 steps. We say 0. In quotation marks, not a labor force participant, 1, in quotation marks, labor force participant. The next step is we need to paste on the value label. So this is like a name tag. We've written the name tag. We need to place the name tag on our variable. So we say label values LFP, the variable, with LFP label. Finally, we tabulate the new variable, and we can see that it looks nice and pretty just like this. So we also want to go ahead and verify that some of our properties hold true. So let's show that those mathematical results hold true. First, if we look at the tabulation of the labor force participation variable, we can see that the percentages here tell us that 34.78% of people were not in the labor force, 65.22 were. Then if we summarize the labor force participation variable, we see that the mean is 0.65217, which would round to 0.6522. And then as a percent, that's 65.22. So the percent of people that are labor force participants is also the mean of the variable because we coded those people as 1. If we coded those people as 0 and the non-participants as 1, the mean would be this, by the way. And you can see that I also did this here. So there's 3 ways to check this, basically. Let's go ahead and also verify that the variance is indeed this quantity here. Now, this is a really specific quantity, but it's kind of interesting to note. I've never actually seen this proof before, but it was something that I was thinking about a couple of semesters ago, and I just did a little arithmetic and proved it to myself. So the point here is that this bias term, you can see that as n grows infinitely large, or let's just say it's, a million. So this is a million over 999,999. This is going to be extraordinarily close to 1. And so basically the sample variance is effectively p hat times 1 minus p hat. Now the hats here mean estimated. So what that means is that we don't actually have the true proportion or probability in the sample. We have an estimate thereof, and so we denote that with hats, just like we've seen before. So this bias term is really not important in practice, but it's useful for proof in the appendix. So we can show, though, with the basic summary statistics and data that this holds. So we summarize the labor force participation variable with the detail option. It prints the variance here, and then we can see if we say display the mean times 1 minus the mean times the sample size over the sample size minus 1. This is exactly the same thing. There's actually no difference. And I'll even show a little bonus here. So we can prove in Stata that these things are exactly equivalent using a kind of funny command that we don't often use. So we're going to use the auto data set just for convenience, which has a dummy variable here. It's foreign. So we can say sum foreign d. And you can see that this means that the proportion of foreign cars in the data set was about 30% with rounding. And the variance happened to be this. Now we can write the same command here. So we'll say display r mean. Let's write it like this. Times 1 minus r mean. Then multiplied by rn divided by rn minus 1. Got to keep track of our parentheses pretty carefully there, so we'll hit that. Whoops, and we actually did make a mistake. Let's see, do we have too many? Oh, maybe we had too many. There we go. Okay, so finally we can go ahead and use this interesting Stata command. It's called assert, and we're going to assert that this here is actually equal to this here. So we need to be able to say that in a statement. We're going to say we found that the code worked, so one reason for putting this up was just to show that this actually works. So we say assert, and we're going to say assert that this equals this here. And there's no output, but that's actually a good thing because assert only returns output if something is wrong. So for example, assert 2 plus 2 equals 5, assertion is false. And we can actually look in the help file and see here that this is kind of useful. So basically it tells us that if the expression is true, the command produces no output. There's probably a way to produce some output if it is true, but I'm not really sure. It's a useful command in programming sometimes. Okay, so that's enough Stata for now. So I wanted to also talk about another use for indicators. So we saw this nice usage before where we basically had, just the simplification of a two-way table. We might also be interested in comparing the value of a quantitative outcome variable across multiple levels of a qualitative predictor. So that's possible with the small number of outcomes in the predictor, but it can sometimes be excessive. Here's an example that's really not too bad, but you can see how other qualitative predictors could get bad. So this is conditional means of metal content of urine, micrograms per liter by race. And you can see here, predictably, there's some evidence of what people might refer to as environmental racism, Mexican American, and then black non-Hispanic individuals had significantly higher group means of metal content of their urine as opposed to, in this case, this would be non-Hispanic whites. This color actually is a little bit off here, but this matches other Hispanic and this matches other race. So something wrong with status coloring scheme there. So anyways, the point is that this is not totally prohibitively difficult, but we'll see later on that, especially if we want to test these things individually, this implies a lot of conditional tests, right? So you can see here we would have to test all of these things like this. So there's all these group-wise comparisons, which is a little bit frustrating, right? If we really did want to sit down and think about how many of them there are. Maybe not frustrating if that's our true intent, but what if we're just interested in something like environmental racism, right? So we just want to know if whites and non-whites have different or similar levels of heavy metals in their urine. And in this case, I think using a dummy variable for white versus non-white brings things into clearer focus. And here we can just print the summary statistics that the mean of y bar just generically denoting the outcome, of content, whoops, sorry about that, is 6.64, which is significantly higher than for whites, which is 5.96. So this makes the analysis pretty easy to summarize. Note, by the way, that the difference is 0.68. That'll come back up a little bit later. So note that we could directly take the difference in means with, for example, tab categorical variable, sum continuous or outcome variable. But we can also use regression, and this is much more useful in the long run. So entering a single indicator variable into a regression model gives the estimated difference in means, and the intercept is the reference group mean. So again, note that we can think about regression here as basically being this procedure. Now, this is not actually a very informative picture, of course. Why? Because there's no actual variation in the x apart from non-white versus white. But the idea is that we can still fit this regression line, and you can kind of see visually that the slope should be the difference in means. There's a detailed proof given in the appendix that requires some knowledge of how we write the variance at high levels. But you can also think about, and this is kind of a funny case, where a really deep intuition actually kind of helps us with something simple. So I know in particular, the TA for this course, David Scallender, has given a really wonderful demonstration of how regression is an attempt to basically fit a set of means across values of a variable, right? So regression actually asserts, the model asserts, that apart from random error, basically we can know the conditional mean at the population level for all possible values of x. In other words, that means that we can say, or what we are asserting, this may or may not be true, is that y is a linear function of x, meaning that at some value of x, as you go from value x1 to value x2 to value x3, the group means of y at those values should always be the same, just multiplied by some constant, right? So in other words, if you have, say, income at x1 and then income at x2 and income at x3, what we're asserting with that linear regression model is that at each value of x, we're going up by a fixed amount. That's what makes it linear, or one thing that makes it linear. There's another totally different perspective on why it's linear that I've shown before with vector space, but we're not going to worry too much about that. So what does that mean here? Well, this is really easy, right? How would we best estimate the conditional means for these two groups? A classic problem in regression is that we actually are sometimes, by forcing the residuals and the predictor to be uncorrelated in the overall, like the entire sweep of the graph, we're going to have regions of the graph where it's clear that the predictor and the residuals are correlated. So the graph overshoots and undershoots in some places. And that problem can be especially fiendish if we have, say, like a sinusoidal or a cyclical trend. So that's a typical problem of regression, right? There's parts of the graph that appear to have clear relationships between predictor and residual. The regression line is just wrong in that region. It's too low here, it's too high there. And we really only don't face that problem when we have really, truly linear relationships between two variables only. Otherwise, we need to enter more variables in. But in this case here, this is actually super simple, right? Because we don't have any option. We have to fit the point of like where would the best place to minimize the spread of the points be for non-whites? Well, we've proven before in class that that would be the mean. The mean is a loss minimizing argmin, as we call it, or in other words, the mean is the argmin of a loss function for a single set of data. It reduces the sum of squared residuals for that data. It's the minimizing value, actually. And the same is true for whites. And so it's pretty intuitive that the regression line should pass through these points, 2 points define a line, and then we're done. So regression is actually super simple in this case. Now the picture isn't very pretty, but I think it makes a ton of sense. So let's show what that looks like in Stata. So notice that before we said that let's go back and look at the numbers one more time just so we can prove this. So remember, here was our regression equation. It was negative 0.68x plus 6.64. Low correlation, but that actually makes a lot of sense here because we don't have much variation in the x. So this isn't a big deal. Again, the point at higher levels is to enter this into a regression analysis with many variables. So how do we interpret this? So we would say that the effect of changing one's race from non-white, which is the reference category, to white, is roughly a decrease of urine metal content of 0.68 micrograms per liter. We see that number here in the regression output. So the slope on white is negative 0.68 and change. So that means that going from, effectively, as you increase the value of the variable white from 0 to 1, that means that the outcome is predicted to decrease by 0.68. That's the effect on the outcome predicted by the change in the predictor. So then, how would we interpret the intercept here? Well, if we write out our regression equation, we would see that, okay, when we have a 0 value of x, that means that the person is non-white. So this is going to be the mean for non-whites. And you can see here that this is 6.64, which is the same number that we got up here. And also, importantly, it's the same number. I guess showing this isn't that informative because I got this from regression. I got this from basic, like the code shown. Where did I show it? Sorry. This here. So tab cat var sum y var actually is what produces this output here, and it's the exact same. So the mean for this group is 6.64, and then if we wanted to find the mean for whites, we would simply add these two things together, and this is the difference associated with the change of race status from non-white to white. So the mean for whites is going to be a little bit less, probably like 5.96, something like that. Here's another example. So this is kind of a boring case, but it's meant to be easy on purpose. So do married people have bigger households? This is kind of an interesting question. And again, I kind of excerpted some GSS data here, excerpted Stata's output here, just so that it's really easy to see the only thing you need at this level from the regression analysis. Apart from the correlation coefficient, it's the coefficient on married and the coefficient on the constant, which is the intercept. So, does this give us evidence that married people have bigger households where home pop is the size of the household? Recalling that the intercept is the mean for the 0 group, and the variable is called married, I made it. So I made it according to standard dummy variable conventions. Let's infer that 0 means unmarried. So then the mean number of people in the household for unmarried individuals is about 2, almost exactly. But then, if we think about the fact that the slope for the 1 group mean the slope here is the difference between the 1 group and the 0 group, that means that we have an associated increase in the mean number of people in the household of 0.76, almost a full person, when you go to being married. So the mean of married people is about 2.78, somewhere in there, right? In fact, it's going to round to 2.79. So that's how we can kind of use this information to say, yes, it appears that there is a difference between these two groups. And by the way, this is the syntax from before that I showed: tab categorical variable, sum quantitative variable. So here I tabulated married, and then I summed the number of people in the household. And you can see that this is the same output from regression, right? So if we just add together this and this, that gives us this here. I'll show that briefly in Stata here because I realized that it wasn't quite included in the comments. So let's change the directory to... Okay. I forgot that I had to make the married variable. Okay, well, I'll show you how I do that. So we do it like this. This is good practice. I'm just going to paste this into the do file. but you can see that this goes through all the steps from before. Actually, maybe I'll show this. So first we describe marital. So we see that the value label is marital. Then we list that label out so we can see all the values. We see 1, 2, 3, 4, 5 corresponds respectively to married, widowed, divorced, never, separated, and then never married, then a missing value. We're going to say generate married equals marital less than 2. So what that's going to do is assign people who have value less than 2, there's only one way for that to happen, equal to married. Now I want to show you why we need to do this replace married equals dot here. So now let's tab married. We'll add the missing value option here. Now, and let's tab the original one, marital. And we need to add the missing value as well. So note that 2 people said on the original marital variable that they had a missing value. They didn't respond to it. But when I had this married option here with the missing value option included, there was no one that was missing. That's bad news, because that means we somehow assigned someone who was missing on the original variable to an actual response on the new variable. Here it's a small distinction, but it can be very big in some cases. So what was the problem? Well, again, Stata is figuring out here that effectively the people that are not applicable or answered not applicable, Stata is inferring that because they have this dot associated with it, so there's this dot n, Stata thinks that's an arbitrarily large value, which is a very weird Stata gotcha. So what we need to do is actually assign people to dot if they were missing. So Stata also knows that this means missing. It's a little confusing. You could do it in this way too. So you could say replace married equals dot if missing, if marital is say greater than, what's the largest value, 5, so let's just say greater than 1,000. And you can see that that actually makes these 2 changes, right? That's pretty remarkable. So what that confirms is that the not applicable here, these people are being internally represented by Stata, even though their dot ends and they have a value label of not applicable, as being arbitrarily large. So that's something to be aware of. And then finally, we can do the regression analysis, and then this gives what we saw before. Finally, the other thing I was mentioning, we say tab home pop sum married, and that gives this information here. Or wait, sorry, I meant to do that reverse. Tab married sum home pop. Okay, this is the output. This actually also works here because home pop is a highly discrete quantitative variable, and we can summarize married. It's a dummy variable. This actually is kind of interesting. It just reverses the analysis, but it's saying based on the number of people in the household, what was your marital status? And you can see that the marital status that, or the number of people in the household that had the highest conditional probability of having married people was 2, followed by 4 and 5. And also, well, sorry, 6 and 7. I missed these. 6 and 7 are actually highest, but then those are, kind of follows because usually people that have that many children typically have gotten taken the trouble to get married at that point. Okay, so that's enough actual demography. Let's go back to the analysis here. So we're going to pick up with this here, and this is kind of where we'll leave off. I need to go actually teach this class, then I'll finish the recorded lecture. So at a higher level, the use of dummies for regression is this. Including regression dummies for all but one group defined by the original variable m, standing for many, is a form of control. So in this case, I regress urine metals on ethnicity, and there's this fancy Stata syntax you can use where you don't actually have to make a set of dummy variables. You can tell Stata to do it for you. I don't show that at this level, though, because it just leads to chaos. You have to have a fair appreciation for how Stata programs. And this also doesn't do it permanently, by the way. This just does it for regression. You can automate the production of dummy variables in Stata, but I would be careful about that. So here are the groups. We've got Mexican American, other Hispanic, non-Hispanic, Black, and other race or multiracial. So we're using whites as a reference category. And that means that the slopes here express the difference in the mean urine metal content for each group vis-a-vis whites. So you can see the group that differed the most from whites was Mexican Americans, which we saw before. You could also put in different reference groups. So by changing this syntax here to say IB1 or 2 or 4, 5, or 6, you could get these other reference groups here, and then the slopes would be the difference from all the other groups to the reference group. That's at a higher level, but I thought I would mention that because it's a technique whose results you've doubtlessly heard quite a bit about in the media. With that, I'm going to pause here because I have to go now teach this lecture live, and then I'll finish the small remaining bit of the recording later. Thanks. So I want you to note that dummy variables can also be used to form simple controls. So even before you get to multiple regression proper, although this is actually a form of multiple regression in kind of disguise, dummy variables allow for stratification of analysis on qualitative variables. You can do this with any qualitative variable, but when you do it with the qualitative variable that's got many possible values, effectively what you have to do is create a set of dummies. Many software packages automate this, but it's good to understand what's happening underneath the surface. So we looked at differences in group means or regression only on a set of dummy variables, but we can also fit different regression intercepts. So we can do regression on a set of dummy variables and a quantitative variable and their interaction. And what this looks like would be something like this. So this is a nice representation of the estimation for effectively what happens when you run that kind of model. So a set of dummy variables, less one, of course, because of the dummy variable trap, interacted with a quantitative predictor, you can actually end up with this nice situation where you're able to estimate whether or not, say, a basic quantitative relationship, one we've seen many times in this class, that between father's education and one's own education, differs by someone's race group. And here we can actually see, although I didn't show you the statistical part of this, that there is a statistically significant difference, estimating with the GSS, of the relationship between education of oneself and education of the father, sorry, I said that very awkwardly, by race. And so you can see that here in this scatter plot. It's a little bit tough to tell, but you can see that these all feature different intercepts and different slopes. So that's a really interesting thing you can do with dummy variables. So just as a reprise here, why do we use dummy variables? It does away with the problem of directionality for nominal variables. It does away with the problem of unit distances for ordinal variables. And for our class, it helps us with, say, data analysis project type 2. It can make two-way tables easier to interpret. It also makes differences between conditional means easier to interpret. And if you do decide to have a qualitative outcome and a quantitative predictor, it eases the pain, so to speak. By the way, for people in my class, you want to check out this handy matrix that I made here that gives you some information, say if you're doing a quantitative analysis or a qualitative analysis, or possibly a quantitative analysis. These are the three that I would recommend. The qualitative outcome quantitative predictor is a little bit tricky. I am actually going to show you right now how you might do that, but this can be considered bonus material for this class. So what you might want to do in many situations is analyze the relationship between a binary outcome or a qualitative outcome and a quantitative predictor. And we can see here that if you just hone in on the indicator outcome, so the red dots there, and the quantitative predictor, this is just kind of a silly example, the scatter plot looks kind of funky, right? We can actually overlay a regression line here, but it's really not super informative because you can see we've got this kind of funny shape of the scatter plot. Nevertheless, you can do regression of a qualitative outcome on a quantitative predictor, and there's all kinds of situations where you may want to do that. For instance, predicting whether or not someone will be married as a function of their income. And there are ways to do that in reverse too. So you can use someone's marital status to predict their income. And in many applications, like for instance, the correlation coefficient between those two things will be the exact same just by laws of the correlation coefficient. So you have some other options, but you may want to conduct a regression analysis where you do have this dichotomous outcome or some kind of other qualitative outcome. So my first piece of advice here would be that you should seek to turn your qualitative outcome into a dummy variable because it makes the regression analysis easier. Now, nevertheless, this is still a little bit of an awkward procedure. So why is that? Well, when we fit this regression line here, note that we are going to get all kinds of predictions that are impossible, strictly speaking, right? So we can say, for instance, that for some value of x here, you will have a prediction, y hat, that is somewhere between 0 and 1. And let's actually show what that looks like in Stata. So why don't we decide to predict using the auto data set whether a car is foreign or not. So we'll regress foreign, which is a dummy outcome. I'll show that briefly, by the way. So you can see here, now if we tab foreign with no label, we'll see that this is a classic dummy variable. So let's regress foreign on price. So we'll see if being an expensive car predicts whether or not the car was foreign. Again, that's not really a causal analysis, but it may be the type of statistical analysis you wish to do. And it does appear to be the case that there is no relationship here. Let's pick one where there is a relationship. And this data set is, by the way, semi kind of cleaned up. So let's try MPG. Okay, we do see a relationship here. So this tells us that the miles per gallon increases as the, and this is kind of the tricky part, right? How do we actually interpret this? It's a little bit tough at first because we naturally want to say as the miles per gallon of the car increases, so you take a unit increase, the car gets more foreign, but that doesn't really make any sense, right? If we throw up a scatter plot here really quickly, so let's do that now. Oops. Sorry, I keep misspelling words here. So if we pull this up here, you can see, all right, so I kind of get the sense that there's a relationship, but what do these predictions mean, right? So going from 20 to 21 miles leads to about a 0.03 increase, but in what? So this analysis is really nonsensical unless you think of it as modeling some kind of underlying propensity or probability. And indeed, that's what's happening here, except I've gone ahead and illustrated with this faked set of data a funny case where we would actually somehow know the underlying unobserved probability. This is known as a linear probability model, and the way that we would then interpret that coefficient is that a unit change in x leads to a 100 times b, where b is the slope here, increase in the probability of y. So that's how we can make some sense of it. If we did have this unobserved probability here, we would say that, yeah, it is the case that, and by the way, these are different sets of data, so this red here does not correspond to this green here. But the idea is that, yeah, when you reach, say, beyond 0.5 probability, you have a much higher chance of ending up here. So what we're doing is we're basically saying when we run this kind of a model, for the regression analysis to make any sense, we believe there to be an underlying probability of the outcome, and that it should be the case that as you get to higher and higher levels of probability, well, you're just more probable of having the outcome, right? But this model doesn't really make any sense unless we assume that. So if we assume that 0 and 1 outcomes are just totally random, I mean, we shouldn't be doing regression in the first place. But also, if we think about there being some other kind of underlying probability model, then this also doesn't make sense. So the regression analysis really can only be made meaningful if we assume that there's an underlying propensity for the outcome, and that is a linear function of x. And so when we run the regression analysis, we are basically modeling that underlying probability. And this would be right here a good best case scenario. So we're saying that basically the probability of our outcome is a linear function of x with some intercept a here, a slope b that's observed as rise over run as we typically think about it, and then there's some kind of underlying Gaussian noise or normally distributed conditional distribution here around the regression line, and that this underlying probability also basically then is what governs the observed outcome. So to make it more concrete, again, if you think about the relationship of, say, like, let's say the one we just looked at here of the origin of a car and then the miles per gallon, what we're saying here is that there's some kind of underlying probability of being a foreign car that is a linear function of the miles per gallon. That's kind of silly, but maybe a better way to think about it where there actually is a causal relationship would be something like, say, your marital status regressed on your income. So we could say that your income has a linear relationship to the probability that you will be married, but probability isn't the same thing as the outcome. So we could say that at a particular point, maybe your income gives you an 80% chance of being married, and that should be reflected in the fact that lots of people with that income are married, but not necessarily everybody. So that's how we would interpret the regression of a dummy variable on a linear predictor, or I should say quantitative predictor. But there are other ways of doing it. So here's a problem with that model. First, we didn't see this so much in the last slide,
but we're going to get some predicted probabilities of our outcome D that are impossible. So for example, in this real world regression from NHANES of the high blood pressure outcome, I just turned that into a dummy on your BMI, we see situations where we have people who have a 150% chance predicted of having high blood pressure. That doesn't make any sense at all. And you can also see here, although it's a little hard because theta automatically cuts the graph off, but if you had, say, like a BMI of 15 or something, which would be bad news, but you could, in theory, also have a negative probability, which also doesn't really make any sense either. So we can see that this so-called linear probability model really doesn't work super great at the extremes, and that might be something that we, don't like. Moreover, and this is kind of related to the problem I'm discussing, we might also just think that there's not actually a linear model that governs the relationship between the quantitative predictor and the probability. So here's an example. Again, we couldn't ever actually observe this, but you could think that you might have strong reasons to expect. When I say you can't observe this, I mean the green dots here, the unobserved probability. You might think, however, that this is a pretty good model, so that there's like some kind of switch point effectively, where as you go along the quantitative predictor, there's a point at which you become significantly more likely to observe the outcome. So there's some kind of a relatively rapid speed up, and that's not necessarily like a super obvious theory of the probability, but the reason that we do this, it's actually a little bit of a cheat in a way. We might think that probability has this kind of sigmoidal function, which also incidentally looks very similar to the CDF of the normal, you might notice. But technically speaking, you can also think about it as a sigmoid function. One nice thing about these functions, though, is that they are bounded. If you ever saw these in Algebra 2, your teacher noted that these are bounded by certain, basically constant values of y. And that's something that we would want to be true of a probability model, because we wouldn't want it to ever be possible to have more than a 100% chance or less than a 0% chance of the outcome. And so that's another reason to like this. And one thing that's a little tricky here is that in this case, I just made this up with kind of random number generators and stata. It's impossible to tell from the actual data which of these would be true, because note here, in this case, I set up basically two relationships of dummy variable outcomes, one on the previous slide, one on this one, and they're extremely closely correlated, so an R of 0.8, and yet they actually come from very different underlying propensities, right? So if we look at this here, you can see in this case, the probability or propensity is a linear function of x. Here it's clearly a nonlinear function of x, and yet the actual observed dummy variable outcomes in red look really similar. So we have to make some strong modeling choices here. What's a common technique at higher levels? Well, we can use the logistic regression technique, or logit, and basically what that does is assert that there is this underlying sigmoidal shape of the probability, which also sometimes is replaced by probit relationship, which is really closely related to that CDF of the normal that I was mentioning before. So how does this work? Well, what we're doing here is saying, okay, let's assume that the underlying propensity that leads to this model has some kind of a sigmoidal shape. And again, the reason for that is nice, because that would mean that it's not possible for anyone to have an underlying propensity of, say, 110% or negative 10%, because sigmoid shapes are kind of naturally bounded here. And you can see that this is basically a simulation or a prediction of that underlying propensity, and you can see that it would kind of have an asymptote here and an asymptote there, which is exactly what we want. So how would we actually estimate this? Well, if we knew every person's actual propensity for D, and we can call it P, which stands for probability, we could actually turn that into a linear relationship in the following way. So note that someone's probability has this interesting shape, right? It's non-linear. So how can we turn it into a linear function? Well, first we can take the odds of it, because note that probability is bounded between 0 and 1, right? So how can we turn it into a linear function that has no bounds? Well, it turns out that the odds of something happening, or the relationship of the probability of the thing to 1 minus the probability of the thing, or Q, actually is only bounded by the negative numbers. So in other words, it can take on any real value. For instance, suppose that you have an extremely high probability of something happening. That would be represented by something like, say, the relationship 0.99 over 0.01. and that's a pretty large number, right? We might actually want to demonstrate that briefly with Wolfram alpha. So let's do that now, and I'll just show you. So the odds of a function, right, we can say y is equal to, and then if we have x over 1 minus x for x between 0 and 1. Note here that, okay, we can't go into the negative numbers, but there's in principle no upper bound here, even though we have this bound on x from 0 to 1, which is a really nice fact. So the odds don't have this upward bound. They still have this negative downward bound, right? So then what we would want to do is take the logarithm, and the logarithm of this thing is a member of the set of all real numbers unless x or p is equal to exactly 0 or exactly 1, but we don't have to worry too much about that. And you may want to think about why that's the case. So if you think about what a logarithm says for some base b of a number a, the answer to that question, let's call it x, or let's call it something different just because we've been using x a lot. Let's call it L. So the log base b of a equal to L means that you take b to L to get a. That's just the definition of a logarithm. So then if we think about that a little bit, well, if the log base b is, like, let's say it's 10, or let's say it's Euler's number, so 2.7, etc., what that means is that we're going to have to take that to some number that is, say, smaller than itself for certain probabilities. For example, let's find out what the logarithm would be of a given probability. So we can write that out here. Like, we're going to say, okay, log, let's say ln. So this is the logarithm with Euler's number of, let's say, a number like 0.5. So a probability of 0.5. And you can see here that that's a negative number. And in fact, this is going to be negative for almost anything, right? So you can see that because even a really high probability, 0.9, that's actually smaller than Euler's number, which is 2.7, etc. We can, Stata makes this a little bit difficult, by the way, but we can come over here and say e to the power of this here. You can see that that's really similar to 0.9. So what that means then is that we can figure out, okay, so for probabilities, these would all be negative. And then for odds, we can say, okay, so for some of the odds, like odds between 0 and Euler's number are going to be negative numbers. And then odds greater than that are going to be positive numbers. So let's think about the odds of 0.9. So that would be a ratio of 0.9 to 0.1. We can put that in here. And we get this number here. So that's a positive number. What if we have exactly matched odds? So that's going to be odds of 0.5 over 5, or 1. And that's 0. So that means that we're going to take the number to 0, right? Then what if we have kind of bad odds of the thing happening? Say 0.33 repeating to 0.666 repeating. This is not exact. People are going to get mad at me, I know. But that ends up being this negative thing here. And we actually already found that effectively. So what that's showing us is that the log odds of an underlying probability can actually take on negative, 0, and positive values, which means that we can actually then say it's not a bounded function. It's going to be a basically linear set of values, or not. It's kind of silly to call it a linear set of values, but that means that that function isn't bounded, and then that would mean that we could express it in a linear regression. However, for that to be the case, we transformed the left-hand side to be log odds. So that means that we then need to come up with a transformation of the predictor. And here the details get a little bit messy, but basically what we do is we take a transformation of the predictor, then we do linear regression, and what that does is give us a set of estimates that would be the coefficients if this were the case, and then we do a little bit of transformation at the end, and we get this set of predicted probabilities here to the right. So this nonlinear model isn't a perfect fit, but it does seem to capture something missing from our underlying linear model. And you can come back to our previous example here and see that the thing to like from this predicted probability is that it can't be greater than 1 or less than 0. And y hat, pardon me, the predictions are more responsive to x in the middle of the distribution, and this is probably a better model of reality, right? It's probably not the case that your probability of high blood pressure is exactly equal across the entire set of real numbers. Why would that be the case? Well, I mean, do you really think, if we go back to that example, let's look at the original data, that your probability of having high blood pressure when you have a BMI of, let's say, going from 41 to, this would be 51 to 52, is the exact same as when you go from, say, let's actually pick a bigger set. Let's say from 40 to 50, an increase of 10. So if your BMI goes from 40 to 50, right, that's an increase of 10. Is that really the same as if your BMI goes from 20 to 30? Well, think about what that means in real terms. Going from 20 to 30 means going from pretty lean to clinically speaking overweight. 40 to 50 goes from being clinically speaking obese, and I'm not saying that pejoratively, that's just kind of what a doctor would tell you, to 50, which is even more obese, right? But if you think about it, you're probably already in pretty poor health when you're at 40. Again, in objective terms, I don't mean to disparage anyone. I will share personally, I've kind of had my own fitness journey as an adult that, I can sympathize with people in kind of all ends of the spectrum here. But if you think about it, that kind of increase is really not the same thing qualitatively, right? We don't want to use numbers to sort of misrepresent a relationship that most of us know is not actually going to be truly linear. So you probably increase your probability of having high blood pressure quite a bit going from 20 to 30, and then from 40 to 50, you already probably have a pretty good chance of having high blood pressure, and you're not going to increase it that much. So this linear model here really isn't very apposite. But if we come back to our situation here, this model would seem to suggest that you actually have a pretty high chance of increasing your high blood pressure or developing high blood pressure going from, say, 20 to 30, as opposed to, say, going from 40 to 50. And actually, you can see it's still going relatively quickly here. That's just how the exact linear model works, or a nonlinear model works in this case. But the key point is that at some point, it does level off. So going from 50 to 60 in this model would not increase your chance of having high blood pressure that much. Going from 30 to 40 here would actually be sort of the rate where you're increasing the fastest, or 20 to 30, 30 to 40. Those both have pretty comparable slopes if we took the basically the approximations linearly in those regions. So that's a nice fact because it seems to fit the model of reality that we might have better. And yeah, the details, by the way, do get kind of messy. So if you actually see a logit model, the tricky part, basically what's happening in that logit model is you don't actually have this underlying probability, so you can't take the log odds of it, right? That's the thing you would need to take the log odds of, but you don't notice probability, you notice the actual dummy variable outcome. So the way you actually estimate this involves maximum likelihood, and it gets really complicated. Basically what you need to do is, again, think about, okay, if I took the log odds of the left-hand side, if I could observe it, what would the right-hand side look like? And then what you need to do is actually transform the right-hand side so that it looks like that. Basically, your coefficient ends up in the exponent of a denominator. Then you run linear regression on that, except to estimate that, you can't use your normal OLS methods, and then you come up with the basically the coefficients in that case, which are kind of hard to interpret. Then you go ahead and you basically have to do some transformations of both sides, and then you get a set of predictions that is this set of predictions I map here. So it's a little bit complicated in the end, but this is a really important technique at higher levels, and I thought people might be interested in it because it flows very naturally from the discussion of dummy variables. Thanks for watching.